Hi, let's write some co-recursive definitions. So these are how we write functions into co-inductive types. So remember that we had this type of streams, which was given by how we can observe its head and its tail, which is another stream, and that it was a coalgebra. So we had this map from streams into something of streams. In this case, it was A times something. And we had, it's not just the coalgebra, it's the final coalgebra, because we have this unfold map, which says that if you have anything else that looks like that, then we get the map into the final one, the biggest one, right? Just given by this function. So now let's write one function. So here I want to take a natural number and I want to make an infinite stream of natural numbers which starting from this number. Right. So let's see if we can do this. I'm going to do this in two ways. First, I'm going to do it using copatterns, and then I'm going to do it using this unfold. So let's start with the copatterns. So here I split on the result. So I have to say what the head of this stream is, and I have to say what the tail of this stream is. So let's think of an example. If the natural number n I'm given is, say, 17, then I want this stream to be 17, 18, 19, 20, 22, 21, 22, and so on, right? Where and so on really means keep going forever, because streams are infinite, right? But that means that my first element, the head of this stream, should in any case be the n I've been passed in. So return that as the head. And the tail, what should it be? Well, if I started with 17, then I want the next thing to be 18, which means that, and that's going to be my next head, right? So if I do up from sac n, that should do the right thing. So here we see that we are really not in Kansas anymore, because we are doing a recursive call on something bigger, right? We're not going down to the base case at 0, where everything will terminate. We are really just counting up. And the reason this is okay is because this is still a productive definition of a stream, right? Because we immediately know what the head is. So someone asks us what is the head, then we can just tell them. And if they ask us what is the head of the tail, then we know that too, because we know what the tail is. And that's fine. That's not a definition that will spin forever, right? We actually can do this. So we do a little test. I will say that do up from 17. Okay, if we normalize this now, then nothing happens, because we haven't asked to observe anything of this stream yet. But if you ask for the head of it, well, then we have this equation here. So if we normalize that, we get 17. If we ask for the tail of it, then all we know is that that is up from 18, because that's this equation. So if we ask for the head of that, then we get 18, etc. Right. So obviously it's a bit cumbersome to do this by hand. So let's define a take function, which takes a finite number of elements from a stream. Right. Yay. And put them in the list. Okay. Note that this function here can't be defined by the defining property of streams, right? Because that defining property gives us functions into streams. But here we want a function out of a stream. And in the same way, it can't be defined by the defining property of lists, because they are defined by functions on lists are defined by pattern matching on the list. So we get functions out of the list, right? But here we want a function into a list. So we really have to define this by pattern matching on the n. It's the only thing we can do. If I try to pattern match on the goal with a copattern, okay, then I get the A. but then it says can't do that. If I try to pattern match on the S, can't pattern match on the coindex type, so all of this doesn't work, right? But what does work, thankfully, is the pattern match on the N. So if you want to take 0 elements, then we can just return the empty list. If we want to take suck N elements, well, then we can take the first one and then something else. What should the first one be? Well, we can take the head of S, right? That should be the first one. And then here we can do a recursive call. We can take N more elements. And of what? Well, if we just say S, then we are going to keep taking the same head all the time. So the right thing to say is tail of S. And this is okay because here we are going down in N. So this is a terminating definition on this natural number. And that's fine because we are fine and necessary because we are producing a finite thing here, right? So we can't afford to keep spinning forever here. If it was going the other way, then that would be fine. It's going from list to streams, because this is an infinite thing. Okay, so now we can take the first 500 elements of this thing. Say. If we can type, and we see that we really get this long stream of things. If we take more, we get more, so it's really infinite. Right? Okay, let's define this in another way. So here I did it with copatterns, which I think is quite intuitive. But now let's do it using the unfold combinator. I want to do up from. And we see that the unfold gives me a function from y into streams if only I give it one of these. So here I want a function from n into streams, right? I want an unfold of something. And that's something. Now, y here is the natural numbers. So these y's are the natural numbers. And it's a stream of natural numbers. So a here is also a natural number. So let's say lambda n goes to something. Okay, and then here I have to give a pair of natural numbers. And how should I think of this? Well, the first one should correspond to what I observe first about this thing, right? So I wanted that to be the n I was given, like that. And the second one should be how to continue. And we saw here that we continue with suck of n. That's going to be my way to continue. And now if I change test to work with up from prime, and it still type checks, of course, but if I run it, then I see I get the same thing. I get this increasing stream starting from 17. So that's another more principled way to write this function, right? I'm using this combinator, but maybe this one is a bit easier to actually understand. Let's do one more example where we are writing a map of streams. If A and B are sets, and if F goes from A to B, then I should be able to take a whole stream of A's and turn it into a whole stream of B's. Okay, and here again, I can't pattern match on the S, right? This makes no sense. This is not defined by constructors. And we see that we really have to do this online as well, one element at a time, because we can't wait for this stream to finish because it never will. It's going to be infinite, right? But again, we are defining a function into a stream. So we can just explain what this stream is by saying what its head and what its tail is. Right? So pattern match, copattern match, like this. And let's see, what should the head be? It should be an element of B. So I can look at the head of S, that's an element of A, and then I can use F to translate it across, right? And then the tail, I should do a recursive call, right? But now I should be allowed to do a recursive call because I'm already explaining what the tail is. So do stream map F And then here I have to think a little bit. It's tempting to just say S, and Agda is not complaining. It's well, productive, so I'm explaining what the tail is. But then when I look at the next head of this, I'm going to get the same head again, right? So I'm just going to repeat the first element if I do this. So the right thing to do is actually to do the tail here. And again, it looks like a more complicated recursive call because we're doing a recursive call on the tail of S, which is more complicated, but that's fine because we are doing it only after we're explaining what the tail of this is. On the other hand, if we add a tail outside here, this is not fine, right? And this is going to be a spinning definition again. Brexit equals Brexit, because we're not making any progress explaining what the tail is. We are saying what it is in terms of other tails. We're not exposing what the head of that thing is, for example. So that's not okay, but this is okay, right? So let's do another test where we take 400 elements of stream map, say plus 43 of up from 42. Okay, so if I now run that, we see that I get 42 plus 33, and then we keep going. So we just applied plus 33 to every element of this stream till we ran out of patience and stopped after 400 of them. Okay, so that's how you define functions into co-inductive things, because that's all you can do. And often you can still get a function out of it because you're explaining how to get it into here rather than out of here, right? But we're still making use of this stream when we define it. So we just have to have something co-inductive around that we can map into, and then we're golden. And these copatterns make it quite intuitive, I think.